So today's learning intention is solving problems with experimental data. Essential skills are working with powers and indices, solving equations, and applying the rules of logs. Example 1. This is an example of exponential decay in a real-life situation. So the mass g grams of a radioactive sample after time t years is given by the formula g equals 100 times e to the power minus 3t. Okay, so part A, what was the initial mass of radioactive substance in the sample? Now let's think about it. At the beginning, initially, when t equals 0. Okay, so the initial mass is found when t equals 0. That's the start of my observations. If I substitute t equals 0 into the equation, that gives me g equals 100 times e to the power 0. That gives me 100, because you need to remember that e to the power 0 equals 1. So the initial mass is going to be 100 grams. Part B, half-life. Now we need to know that the half-life equals the time taken for mass to decay to half its original value. Now you might have seen that in chemistry or physics, but if you don't take that, that's a point in mass that you need to know. It comes up all the time. So memorise that. So the half-life equals the time taken for the mass to decay to half its original value. So e to the minus 3t equals a half. Okay, I'm going to half that 100. I'm going to have to times it by a half. So the exponential function equals a half. Now we saw in the last video how to solve for unknown exponents. We take the logs of both sides. Now you can either take log to the base 10 or the natural log. I'll take the natural log of both sides. And remember, to solve it for t, I'm going to use the rules of logs and bring down the exponent minus 3t and multiply at the front. So I've got minus 3t times log e to the base e equals log of a half to the base e. I want t on its own. Okay, so now I remember also that log e to the base e equals 1, so that kind of vanishes. And I've got minus 3t equals log a half to the base e. And then I have to divide by minus 3. Use a calculator to get the answer. And I've got 0.23 years. Right, time for example. So example 2 is an exponential growth example. So it says the world population in billions t years after 1950 is given by p equals 2.54 times e to the power 0.0178t. Part A, what was the world population in 1950? Now the question says in 1950 was the beginning of the question, it's the beginning of observations, everything was after 1950. So the initial population at time t equals 0 is going to be 1950. So that gives me the population p equals 2.54 times e to the power 0, which just equals 2.54 billion, because the question says it's in billions, not just people, and that's because e to the power 0 equals 1. Again, it's just the multiplier, it's the number before the exponential function, that's always the initial value. Part B. It says find the nearest year the time taken for the world population to double. So time taken to double means if I want 2.54 billion to double, then e to the power 0.0178t must equal 2. Now to solve that, again, it's an unknown exponent. I'm going to take logs of both sides, and you can decide whether you want log to the base 10 or the natural log. I'll go for the natural log, so log of both sides. Again, solving for t, I'm going to use the rules of logs and bring the exponent down, so 0.0178t times log e to the base e equals log 2 to the base e. Now remembering that log e to the base e is just 1, that's going to vanish. I can rewrite that as 0.0178t equals log 2 to the base e. I'm solving for t, I'm going to divide by 0.0178, and that gives me 38.94. But the question says I want the time to the nearest year. I'm going to have to round that up to t equals 39 years. Right, try these on your own. Example 3, example 4. Example 4 is a past paper for 5 marks. So take your time, use your notes, try and solve that on your own. Pause me for the moment and then come back and I'm going to talk you through it. Right, example 3, time to look over it. So the number of bacteria of a particular strain is given by this function. B is a function of time equals 45 times e to the power 1.5t, where time t is in hours. So at the beginning it says how many bacteria are there at time 0. So t equals 0, bacteria equals 45 times e to the power 0, which is just 45, because e to the power 0 equals 1. The next part says, how long will it take for the number of bacteria to treble? So if I want to have 3 times 45, then e to the power 1.5t must equal 3. Same way, rows of logs, take logs of both sides. Rows of logs, the exponent comes down, so 1.5t log e to the base e equals log 3 to the base e. Remembering again, log e to the base e equals 1, so that vanishes. That can be rewritten as 1.5t equals log 3 to the base e, and then dividing by 1.5 to get my answer 0.73 hours. Example 4 is the past paper. So a researcher modelled the size n of a colony of bacteria t hours after the beginning of her observation. And n is a function of t equals 950 times 2.6 to the power 0.2t. Part A, what was the size of the colony when observations began? Again, you know it's just a multiplier. You can just write down 950, or if you can't remember that, just go through the process. T equals 0 for initial size, so I've got 950 times 2.6 to the power 0, which is now 950 because 2.6 to the power 0 equals 1. So part B, time taken for the size of the colony to be multiplied by 10. Well, that means that I want the exponential function 2.6 to the power 0.2t equals 10. Take logs of both sides. Now just to change it a bit, I'm doing log to the base 10 of both sides. Rows of logs bring the exponent down, so 0.2t times log of 2.6 equals log 10. Now they're both to the base 10, I've not put it in there, but it's just your log button is log to the base 10 in your calculator. I want time on its own. I divide by log 2.6, work out what that is, 2.41 in my calculator, then I have to divide by the 0.2 to get time on its own. So time is 12.05 hours, and that'll be your 4 marks. So how did you get on? Okay, if you've got a mistake, where's your mistake and why? Make sure you've understood how I did that. Right, to analyse how you did, self-assess your progress. Red, amber, green. Remember, if you're struggling, make that known to your teacher as soon as possible. If you'd like to try a couple of more examples, then turn to your textbook, page 299, questions 4 to 7. Mark them from the back of your textbook. So what have we learned today? Well, we learned how to solve problems with experimental data. Very similar to what we did with unknown exponents, but just putting in a wordy problem in a real life context for you. So you have to use the rules of logs, simplify the equation applying 1 or 2 of the rules, take logs of both sides to cancel, look out for quadratic to solve, in this case not so much.